Today we are looking at combinations. Yesterday we talked about permutations. A permutation is a way to select things in a specific order. And it counts up how many different orders that we could put things in. So one of our examples yesterday talked about 12 skiers in a competition and how many different arrangements would there be of specific places. In a competition, it means something different to come in first place or to come in 12th place. Okay? A combination is when we're making selections, but the order doesn't really matter. So if it doesn't matter whether you get picked first or picked last, it's more like a committee. Just everybody's going to be working together and you don't have specific roles. So it doesn't matter who gets picked and who gets first and who gets picked last. So in a permutation, order matters, and in a combination, the order of selection does not matter. The formula for a combination is very similar to the formula for a permutation that we looked at yesterday. We didn't really use the formula. We used our calculators, or we used that blank method where we wrote out how many blanks and counted down our numbers in there. But the formula here is very similar. What the formula for a combination does is it takes, this actually means a permutation, and then it divides out this r factorial, which is the number of rearrangements. So the same three people but selected in a different order doesn't really make a difference if they're just on a committee. It doesn't matter who gets picked first and who gets picked last. Okay? So this option will be in your calculator in the same menu that the permutations were yesterday. So whatever type of calculator you had, you can find the option for a combination in the same place. Yesterday I mentioned that the default, the standard calculator that comes on iProducts doesn't have this, but last night I did a quick search on the App Store and I just typed in like free scientific calculator, and a lot of them do. So I just looked at the screenshots and made sure that it had buttons that said the NCR and the NPR, and then those are good calculators. If you want to use your phone to do them, that would be fine. So in our first question, it says a standard deck of 52 playing cards has 4 suits, each with 13 different cards in a suit. If you are unfamiliar with what a standard deck of cards is like, in your packet, I think it's like a couple pages over, there's a chart that just kind of shows how a deck of cards is built. Half of them are red, diamonds and hearts are red, half of them are black, the clubs and the spades, and then it counts up 2 to 10, and then there's aces, jacks, kings, and queens. So if you're unfamiliar with your cards, you'll want to use that chart when thinking about some of your homework questions. In a lot of games, it doesn't matter what order the cards are dealt to you in, because once you get your cards, you're just going to rearrange them in your hand. So it doesn't matter which card you get first and which card you get last. So that means these are problems for combinations. So the first question says, if the order of the cards is not important, how many different 5-card hands are possible? The first number is the number that fit our requirement. So in this one, we weren't really given any specific requirement, just that we're drawing 5 cards, any 5 cards from the deck. So the whole deck of 52 cards will work here. Then we use C for combination, because the order doesn't matter, and we're drawing 5 of them. So the first number is the number that works for the requirement. There wasn't a requirement here other than that we're using the standard deck. The second number is the number that we're picking. So then in your calculator, wherever you found your stuff yesterday, you can find this new option of combination. And we find that there are over 2.5 million different 5-card hands. So the second question asks, and how many of these are all 5 cards the same suit? So what we need to do here is first decide which suit. So how many suits are there? 4. So of the 4 suits, we need to pick one suit to go for. So it could be any of them, hearts, diamonds, clubs, spades, but we have to pick a suit and stick with that suit now. Within that suit, how many cards are there? 13. And from those 13 cards that now fit my requirement, I need to draw 5. So we can type that in the calculator then as well. If I can hit the right buttons. And get 5,148. So not very many different ways to get 5 cards all the same suit. That hand is typically called a flush. And in poker, it's considered to be a very good hand. And the rank of hands in poker was not randomly selected, like somebody thought, like, hey, well, this is kind of a cool thing, we'll call that a good hand. The way that those were determined were based on how easy it is to get them. And so with only 5,000 of these out of 2.5 million different possibilities, it's pretty unlikely that you're randomly going to get the right 5 cards here. So that would be considered a good hand. Questions? The next question looks at, really it's basically the same question, except we're drawing 7 cards instead of drawing 5, so just change the 5s to 7s and it's good. So instead of looking at this same example, I want to look at something that's more similar to your homework, a couple of the problems there. So I want to know how many different 5-card hands there are where all 5 of the cards are what we call face cards. So I want to know a 5-card hand, all face cards. Those would be ones that have faces on them. So jacks, queens, and kings have faces on them. So how many face cards are there in the deck? If it's jacks, queens, and kings, how many of those total are in a deck? 12. There's 4 suits. So there's the hearts, the clubs, the diamonds, the spades, and within each of those suits, there's 3 cards that have faces, so 12 face cards. And again, that chart is in your packet. If you're uncomfortable with decks of cards, you can look at that chart there. So when we do these combinations, the first number is the number that fit the requirement. So the requirement is face cards. There's 12 of those. Then the second number is how many we're actually drawing. So how many are we drawing? 5. 5 face cards. So we want a 5-card hand that all of them are face cards. So the first number is how many fit the requirement. The requirement's face cards. There's 12 of those. The second would be how many we're actually drawing. We're drawing 5 cards. Okay. So the next problem I want to think about is what would, how many possible hands are there that are 4 of a kind? So that 4 cards are the same, and the other card is not the same because there's only 4 of each kind. So if I get 4 cards that are the same, and then the other one is whatever. Okay, so 4 of a kind. And then one other. So the first thing I need to do is pick within a kind, how many are there? So within one kind, so let's say my kind is kings. How many kings are there? 4 of them. And how many am I picking of those kings? All 4 of them, so I get 4 of that kind. So of the 4 kings, I want 4 of them. But I just said kings. How many different kinds are there? How many different kinds of cards are there in the deck? Look at your chart if you're unsure. 13 different kinds. There's 2 through 10, ace, jack, queen, and king. So there's 13 different kinds, and we could have picked any one of those kinds. I just said king, but jacks would be fine as well because this just said 4 of one kind. So any of the 13 kinds would have been okay. And then within those, I wanted to take all 4 of those. Well, that covers the 4 cards, but now I need the one other. So once I've taken those 4 kings out of the deck, how many other cards are there? 48. There's 52 cards in a deck. So once I've taken out those 4 of whatevers, there's 48 left. And how many of those am I grabbing? 1, because and one other. So those first two parts, select my 4 of one kind. I'm taking 4 cards out of 4 of one kind out of 13. And then that last part says, out of the other 48 cards in the deck, I'm going to grab any one of them. Okay, and that would give me, how many different possible hands would give me? 4 of one kind. Okay, so you'll have some card prompts in your homework that are similar to those. A restaurant serves omelets that can be ordered with all different ingredients here. Suppose you want exactly 2 vegetarian and 1 meat. How many different types of omelets can you order? When you order your ingredients, it doesn't matter what order you say. If I tell the waitress that I want green peppers and ham, or if I say ham and green peppers, I'm going to get exactly the same omelet. So the order does not matter, so this is where we would use a combination. So, how many different vegetarian ingredients could I choose from? So I've got green pepper, red pepper, onion, mushroom, tomato, cheese. So there's 6 vegetarian ingredients. And from those, how many am I going to pick? 2. And when we say the word and in a probability or counting problem, we're going to multiply. And I want 1 type of meat in there. So how many different types of meat could I get? 4, ham, bacon, sausage, steak. So out of the 4, I'm going to pick 1. Okay, and we can do that on the calculator in the same menus that you went to yesterday. We're just going to choose the C option. So of the 6, choosing 2, the 4 choosing 1, and we get 60 different omelets that we could end up ordering that way. Questions on that? Part B, suppose you can afford at most 3 ingredients in your omelet. So you look in your wallet, the amount of cash you have, and what the menu says. You can only afford to get 3 different ingredients. So how many different types of omelets can you afford? Well, this doesn't make a distinction between meat and vegetarian. So how many different ingredients are there? 10. So of the 10, I can pick 3. But just because I can afford 3 doesn't mean I have to buy 3, right? If there's not 3 that look good in that list to me, I don't have to get 3 just because I can afford to get 3. So I could say or, and when we use the word or in a probability or counting problem, we're going to add. I could just pick 2 of them. I could just pick 1 of them. Or I could pick to have no ingredients, which is really just an egg, so I wouldn't so much call that an omelet, but it's an option. And so we could calculate each of those individuals and then add them together. When it says at most, that means you need to consider the options of not taking the full amount. So we don't have to buy 3 just because we can afford 3. As a note, if you can remember for quicker calculation, whenever you're choosing 1 out of a given value of things, there are the first number of ways to do that. If I have 10 things and I need to pick 1, there's 10 different things I could pick. Whenever the last value is 0, it doesn't matter how many I'm choosing from. There's only one way to pick nothing, and that is to pick nothing. So when that last number is 0, you're always going to get a 1 there. So if you remember that, then it saves you some typing stuff into the calculator. If not, you can always just type it in the calculator. So you get 176 different omelets we could afford then. Questions? As many as 5 different cities and 7 attractions within those cities. Suppose you want to visit exactly 3 cities and 4 attractions. And order doesn't matter here. It doesn't say that we're necessarily planning our route, so we're just kind of picking which cities we want to go to. How many different trips are possible? So since order was not mentioned in here, this is a combination problem. So I want to go to 3 cities. How many cities could I go to? 5. So from the 5, I'm going to 3. and that word and means multiply, of the 7 attractions, I want to go to 4. Okay. So and means multiply, and we consider each thing individually and then just multiply those results. So that gives us 350 different trips we could plan. Suppose we want to visit at least 8 locations. Cities, attractions, doesn't really matter, but we want 8 things on our agenda. How many different trips could we do? So we're going to choose from 12, adding up our cities and attractions together, and we can go to 8. 8 would be fine with us. But it says we want to visit at least 8 locations. So 8 would be okay with us, but how many else would be okay with us? 9 would be okay with us. 10 would be okay with us. 11 would be okay. And 12 would be okay as well. At least 8 means 8 or more. So I'm okay going to 8, but I'd be fine having more stuff on my agenda as well. So the first few I'm going to type in my calculator. So 12, choosing 8, gives 495. Choosing 9 gives 220. Choosing 10 gives 66. But these last couple I actually don't have to type in. Again, if you just kind of remember this, it saves you some typing. If the difference is by 1, okay, so 12 is 1 bigger than 11. So if you're picking everything except for 1, there's the first number of ways to do that. And the last one, if you're choosing everything, there's only one way to choose everything. That's to choose everything. We're not leaving anything out there. So if you remember those, it just saves you a little bit of time in terms of having to type those in the calculator. But if not, you can always just type them in. So that would be 794 different trips we could plan. After staging a series of 12 different plays, you want to attend at least 3 of the plays. How many different combinations of plays can you attend? We can do this problem like the last one. And I could say, of the 12, I could go to 3. Or, if it says at least 3, which way do I want to count? Up or down? Up. So I could do 4. I could do 5. I could do all the way on up to going to all 12. That seems like a lot of calculations to make. That'll work. There is a faster way where we won't have to make as many calculations. And that's to think about this list of all the plays that we're given. And so for each play on this list, we're going to look at it and say, do I want to go see Romeo and Juliet? Yes or no? Do I want to go see Les Mis? Yes or no? Do I want to go see Wicked? Yes or no? And for each play, we have to make a choice, yes or no. We only have 2 options. We go or we don't go. So we have to make that yes or no choice 12 times. So that would be 2 to the power of 12. 2 because yes or no. 12 because that's how many times we have to make that choice. But in doing this, some things could happen that we don't want to happen. For example, we could say no to all 12, and that'd be a problem because we want to go to at least 3. So what we want to do is subtract out the stuff that we don't want to happen. I don't want to end up going to 0 plays or 1 play or 2 plays because I want to go to 3 or more. So that has fewer calculations but would give us the same answer as the first way. So it's kind of a preference thing. This is a little bit less work to do, but if you're like, I don't know if I really get that, then you could totally do it the first way. It's just going to be a lot more button pushing on the calculator. Okay? But I can do 2 to the power of 12. Gives me 4,096. And then I want to subtract out. Choosing 0 we said is 1. Choosing 1 we said is the front number. And then choosing 2 I'll type in my calculator. And get 66. and then do that subtraction out. 4,096 minus 1 and 12 and 66 leaves me with 4,017 different options we're going to place. Okay. Questions? As the previous one, we've got 6 toppings for our salad. On the menu it says a deluxe can have up to 4. So how many different salads can we make? And again, order doesn't matter here because whenever you tell them what toppings you want, they're just going to throw it on the salad. It doesn't matter what they throw on first. They're just all getting into your salad. So this is a combination. If order of selection matters, then that's when we need to do the permutation that we learned about in yesterday's lesson. So of the 6, we could choose 4. Of the 6, we could choose, let's see, it says on the deluxe we can have up to 4 toppings. So do I want to count up or count down? Down. I could choose 3 toppings. I could choose 2 toppings. I could choose 1 topping, or I could choose no toppings, which is just lettuce. That's boring. And all of that would be our possibilities then. That's one way to do the problem. It's not terrible, but it's still quite a few calculations. Looking at this like the last problem, what we could do is look down the list and say, you know, do I want eggs? Yes or no? Do I want bacon bits? Yes or no? Do I want this? Do I want that? Yes or no? So we have a yes or no choice to make. How many times? 6 times for each of the possible toppings. But we cannot end up choosing all 6, or we'd have to pay extra. And we cannot end up choosing 5, because we'd have to pay extra. We're only allowed to get 4. So then we can do this calculation, which has fewer things to type in the calculator, and get that we have 57 salads. That's the same answer you would get doing it the first way. It's just more stuff to type in the calculator. Questions?